Welcome everyone to our critical design review on our project called C.A.P.E.R. This is our team consisting of 3 electrical engineers, Kellen, William, and Sarah, and our 1 computer engineer, Paco. Our project is on C.A.P.E.R, an acronym for a compact animated parrot with enhanced responsiveness. This is a parrot with a base and realistic body that fuses artificial intelligence with animatronics to create lifelike motions with the head, beak, body, wing, and tail flap, as well as voice response capabilities where C.A.P.E.R will actually talk back to the person speaking to it. Just as automaton, which are incredibly old animatronics created in the 1800s, became obsolete and antiquated, traditional animatronics are soon going to follow suit. The next generation of entertainment-oriented robots will require the newest technology for any chance to succeed. The downside to this is the high cost of production and installation of modern animatronics. It would cost companies hundreds and thousands of dollars to upgrade their facilities to accommodate these new figures, and many companies cannot foot the bill. Most current-day entertainment robots are massive, think Disney, and thus are typically bolted to one spot for life. They are also unresponsive, and with C.A.P.E.R, we plan to change that. This is our motivation for C.A.P.E.R, to create a low-cost, low-profile, portable robotic parrot suitable for permanent installation in facilities with a smaller economic footprint. C.A.P.E.R integrates modern AI and movement control systems for improved human interaction, being able to carry out simple conversations with the user. Voice activation and speech detection will prompt the AI program to generate appropriate movement and audio data in real time. The raw electrical movement impulses will be translated into motion and synchronized with the audio. It will look like you're actually talking to a parrot. There is also the option of traditional control methods, real-time movement control, and pre-recorded sequencing. Our objective is to develop user-friendly interfaces that don't require specialized knowledge to appeal to a wider audience. Simplifying the design and material will also reduce development, installation, and maintenance costs to make it a viable option for smaller venues, schools, and hobbyists. The C.A.P.E.R project is a response to the growing need for ethical and positive application for robots, aimed at moving away from the potential negative uses like weaponization and job displacement, and instead move towards entertainment-based practical effects to once again stimulate interest in the field of animatronics while implementing AI technology. Our goal is to ultimately improve human interaction with C.A.P.E.R and to create an affordable and portable entertainment robot in comparison to existing robots that has a smooth movement and conversational capabilities. It should also be easy to use and switch between the various input modes with a quick response time of within seconds. If time allows for it, we would also like to implement sensors that would create response feedback to touch, lighting, and the presence of humans to make voice responsiveness and movement more dynamic and realistic. C.A.P.E.R's cornerstone component group will be the robotic parrot apparatus that is operated by the control system, referred to as the main body. The main body will contain all of the systems needed to turn the signals from the control unit into movement. C.A.P.E.R will stand at approximately 2 feet tall, with the frame itself being at around 1.5 feet. The internal central frame is made from wood and will support all of the mechanical devices. The internal shaping framework is made from foam, rubber tubing, and metal rods. The solenoids are there to react to signals given from the controller to move the corresponding body part. As mentioned earlier, C.A.P.E.R will showcase 4 movements: the beak opening and closing, the vertical head tilt, the vertical body tilt, and the lateral wing and tail flap. Each movement will be carried out electrically, but without the use of ultra-precise position or speed monitoring. The binary on and off style of movement control makes programming more timely, efficient, and understandable without jeopardizing the realism of the movement. The internal frame of the robot, along with all the devices and physical extremities, will be completely concealed by the exterior skin of the parrot. The figure will stand upright, fixed atop a pedestal for permanent mounting, and wires will run out the bottom of the figure for a connection to a separate control unit. This is what the internal frame should theoretically look like when C.A.P.E.R is opening and closing its wings. This shows the computer model versus the completed real-life wooden central frame. Solenoids allow for direct control from the custom board, and their binary nature allows for an easy programming scheme with the voice response board. There may be some movement inaccuracies, but the compromise in movement accuracy is far overshadowed by the gains of lower cost, near silent operation, ease of control, and simplified controller design. The operation modes C.A.P.E.R will employ are fully manual live operation, partial manual live operation, and pre-recorded sequence operation. The operation modes C.A.P.E.R will employ are fully manual live operation, partial manual live operation, pre-recorded sequence operation, and automatic live operation. The fully manual live operation uses parallel digital inputs, so C.A.P.E.R can be manually operated using push buttons. Pressing a button will activate the corresponding joint movement, and depressing the button will return that joint to its resting state. The partial manual live operation uses the parallel input for the mouth actuator, so the user can plug a microphone into the control board and control C.A.P.E.R.'s mouth with their voice. The remaining 3 movements can still be operated with the corresponding push buttons or be moved automatically using the partial manual mode. By flipping a selector switch mounted on the enclosure of the control board, the user can activate a subroutine within the control board's program that randomizes the head, body, wing, and tail movements, allowing for complete hands-free operation of C.A.P.E.R. For the pre-recorded sequence operation, C.A.P.E.R can be operated like a traditional animatronic using an external playback device. Using any easily attainable digital audio workstation, the user can pre-program a sequence of movements on their computer using MIDI and transmit the data stream onto C.A.P.E.R.'s UART input. Once a stream of movements has been recorded by the user, that exact sequence can be played back repeatedly. The automatic live operation allows C.A.P.E.R to listen and respond using a synthetic voice to users with its speaker and move in time with the voice response. Neither the movement nor the content of the voice response given is pre-programmed in this operation mode.
All right, now that you've been introduced to C.A.P.E.R, it's time to get down to the specifics. Right here is a main block diagram showcasing all of the main peripheral circuits, some of which are included on our custom board and some of which are very close by. As you can see, the microcontroller is capable of decoding and understanding several different classes of inputs and streamlining the signal to one single channel of outputs. This channel of outputs will be sent to the op-amp solenoid drivers, a bank of relays that will convert the low current power from the microcontroller to suitable high current power to operate the solenoids. The custom board that we designed for C.A.P.E.R is called the Input-Output Control Board, or the IOCB. At the heart of the IOCB is our microprocessor, the Texas Instruments MSP430G2553 MCU. This chip is capable of processing both UART signals as well as analog inputs through the various GPIO pins on the chip. As well as the microprocessor, several peripheral circuits will be on our custom board, including terminals for the push buttons, the mode selector switch, the MIDI optocoupler circuit, headers for external debugging using the launchpad board, the low voltage power regulators, and the ham radio style Vox circuit. The 2 block diagrams on the right show the classes of input and output more zoomed in. As you can see, there are 2 classes of input the board will accept: the parallel analog channels from the push buttons and the selector switch, as well as the UART channel. The outputs are then sent through the output pins to the op-amp drivers, as mentioned before. Here is a chart showing all the connections to the MCU. Our board uses the 20-pin version of the Texas Instruments MSP430. This allows for future redevelopment and expansion because 6 of the pins are unused. The 4 push buttons will be spring-loaded so that when the user lets go of the button, the movement will then retract to its resting state. The selector switch, on the other hand, will not be spring-loaded. Instead, the selector switch will be left in whatever position the user would like as long as the user wants. When the user is ready to switch it back to full manual, you just have to deselect the switch. One of the other peripheral circuits on the IOCB is the ham radio Vox circuit. This circuit allows for an external microphone to be plugged in and for the user to toggle the mouth movement using voice activation. The audio from the microphone enters a non-inverting op-amp stage, which gains up the signal to a more usable level, as well as gives a DC offset, so the comparator stage following it has a better time detecting. Once it enters the comparator stage, the comparator will swing high whenever there's voice present and swing low whenever there's voice not present. The signal then passes through a half-wave rectifier, a capacitor to reduce ripple, a current limiting resistor, and a load resistor. This voltage then enters the gate of an N-channel MOSFET that will then switch on and short pin 1.0 on the MSP to ground. This is in fact the same exact pin that the push button uses to control the mouth. Whenever a person talks into the microphone, the mouth will be triggered completely hands-free. Another major peripheral circuit on the IOCB is the MIDI optocoupler. This circuit isolates the ground planes of both the IOCB and the external playback device. On our circuit, we use the H11L1, in our case, the surface mount version. This then goes into MSP pin 3 or pin 1.1, which is the UART RX pin on the MSP. To test the MIDI functionality of our board, I used my Korg Trinity 61-key digital workstation piano. Despite being almost 30 years old, this does actually have full MIDI capability. Since MIDI has been around for over 40 years now, most devices in the musical instrument world use MIDI in some way, which makes it very easy for us to find many different programs that are compatible with C.A.P.E.R. To test the Vox circuit out, I used an MXL LSM-3 dynamic microphone and an XLR cable. Any dynamic microphone would work in this case, like a Shure SM57 or a Shure SM58. This means that we do not need to use an external phantom power supply, which will reduce cost on power consumption and size. Now going on to the software side of things, the microcontroller itself has a program that will allow the MSP chip to decode several classes of input and produce 4 analog pulse outputs for the 4 movements. So the 6 inputs that will be seen by the MSP will be the pulse streams from the mouth, head, body, and the wings and tail, the UART MIDI data stream, and the selector switch pulse stream. The 4 outputs, of course, will be the mouth, head, body, and wings and tail. Every time the IOCB circuit is reset, all the variables are cleared and redefined. This will prevent any glitches that will occur in between startups. Once everything is set up and ready to go, the code will then utilize interrupts to decipher between the different types of input. Using the 20-pin version of the MSP, there are 2 ports available for use. Port 1 contains all of the 4 movement buttons, whereas port 2 uses the selector switch. This means when any of the 4 buttons are pressed, the port 1 interrupt is triggered. This then toggles the port 1 interrupt function, which will then pull all 4 buttons to see which ones are pressed. If a button is held down, the interrupt will immediately raise again until the button is released. In the case of the port 2 interrupt function, whenever the selector switch is toggled, the port 2 interrupt flag will be raised, and the program will enter that interrupt function until the switch is switched off. Once the switch is turned back off, the code will then return to the main, where it will wait there until another interrupt appears. The last interrupt that will appear is the UART interrupt. This is used for both the pre-recorded sequence operation as well as the fully automatic operation. Here in the chart, you can see the 8 different messages which correspond to the 4 different movements, both being turned on and being turned off. Whenever one of these messages is received at the UART pin on the MSP, the UART flag is raised and the UART interrupt function is called. The function will then decode what message has been sent and trigger the corresponding movement. Once this is finished, it will then return to the main until the next interrupt flag is raised.
Looking at our voltage regulators, we used the following chips and modeled them with the following capacitor values from the datasheets to keep noise at a minimum. These voltage regulators will be powered directly from the plus and minus 12-volt power supply and will provide the voltages to our microcontroller and input-output controller board peripherals. Taking a deeper look at our different regulators, we have a plus 5 volt, a plus 3.3 volt, and a negative 5 volt regulator. We are utilizing input headers to supply the voltages from our external power source. The plus 5 volt is a switching regulator while the other 2 are linear. This is because the plus 5 volt regulator has to power the off-board relays, and those can use up to 300 milliamps. These are going to produce a lot of heat, so we will use heat sinks. All voltage regulators will be through-hole. Our project will have a chassis external of the bird. This will store the IOCB, VRB, relays, and the DC power supply. The purpose of this is to protect the circuit board and assist in the support structure. The chassis will be 3D printed to allow for accuracy and precision, and a model is presented below. This is a visual representation of the power supply stream. Begins with the external source that is connected to the 3 different regulators, and then it shows what peripherals each regulator is powering. Below is the dry run of our first PCB design in Altium. We successfully integrated our first schematics, input our component footprints, and routed the board successfully. Upon our first revision with Dr. Weeks, many updates have been made. Many of our circuits were prototyped and advice was given to create a more consistent design. An example of this is that our entire debug circuit was removed. In our new updated circuit, it was replaced with header pins for external debugging using the Launchpad board. This will free up space, improving cost and efficiency. Our updated board will include a ground plane to improve efficiency as well. The current problem with our PCB design is successfully integrating the new component libraries, but once this is completed, we're hoping to have our PCB ordered by this weekend.
The Unified Conversational Module is the main software behind the operation of C.A.P.E.R's conversational mode. It consists of two separate programs that communicate over the internet. These programs are designed to record voice input from the user, process that input to create a sensible text response, and create an audio response that is then sent to the speakers to be broadcast as speech. The VRB, or Voice Response Board, was chosen to be an NVIDIA Jetson Nano Dev Kit. This system was chosen for its low cost, low power consumption, as well as being able to connect to Wi-Fi with the addition of a Linux-compatible Wi-Fi adapter. The software on this board is responsible for recording audio, sending it to the server, receiving the resulting synthesized audio, and creating movement commands based on the characteristics of the audio before sending both to the IOCB for broadcasting. The system is connected to an omnidirectional microphone, which allows it to listen to the whole room similarly to other static devices like Alexa or Google Home. This slide represents the interaction taking place between the voice response board software and the cloud software. It is triggered by speech detection and ends with synthesized audio being sent back to the VRB. The cloud software consists of a compiled CUDA runtime-enabled C++ program that transcribes audio to text, creates a response from that text, and synthesizes the response into a .wav signal. It utilizes three separate AI systems to accomplish this. One is the Whisper Small, which will be used to generate user text from user speech. The second one is Mistral 7B Instruct 4-bit quantized, a large language model used to create the response text. And the third is Speedy Speech, an artificial intelligence designed to synthesize speech using the response text as input. We chose to host all AI systems entirely on our own server due to computational and software support limits within the Jetson Nano Dev Kit. Many of the vector operations needed to compile the system were missing on the Tegra chip, making the cloud our only option. The resulting pipeline is fast, efficient, and effective, allowing C.A.P.E.R to do exactly what it is intended to do. This is some of our sample code. As you can see, this is a callback function for transcribing the audio utilizing the Whisper pipeline. This is the exact way that we call the rest of our software.
All of our circuits have been prototyped and tested up to this point and proven working. However, some slight tweaks have been made just to increase the consistency of our circuits. The PCB design is going through its second revision and will be done within 48 hours following week's revisions. Once the footprint error is figured out, a working board will be created shortly after. The internal frame of C.A.P.E.R is all but built, while the outside is yet to be constructed, as it will have to line up with our motors, the construction of the physical bird, later stage planning. The server software is at a stage where all the AIs have been tested in some capacity, and now we are attempting to compile them all into a single library for increased performance. The voice response board software successfully communicates with the server. Now we must test the security of the function and speed. The Vox circuit is complete and functional, and the MIDI works fine on the IOCB. We just haven't tested it yet with the VRB. In terms of research, we're mostly done. Our parts have been selected and we've compared them. Once the PCB is done, we will have everything in our possession to create the bird. The only tweaks we're making now are what Dr. Weeks advised, or if we're troubleshooting and something doesn't work, we may replace it then. Our design as well is almost done, just perfecting our board layout and increasing the realisticness of the bird. Our parts acquisition is about halfway finished. We have the frame, the solenoids, the Jetson Nano, and everything prototyped. Again, we are waiting on our PCB and the physical bird design materials that we are going to get towards the end of the project. Software is coming along nicely. We have a working LLM model and are fine-tuning the rest. Our testing is currently at a halt as our prototype worked, but we won't be able to test points on our PCB until it arrives. Overall, our project is well over halfway complete, the rest being dependent on the PCB arriving and constructing the physical bird. In summary, as a lot of what I'm about to cover is what I just covered in the previous slide, what's left is finishing and ordering the PCB, completing the code and having it meet our benchmarks, transferring said code onto the boards, physically constructing the hardware, as well as the body of the Parrot. The following are our financials, and you can see we are coming in significantly under budget.
All right, thank you all for tuning in. If anybody has any questions, please let us know. Thank you.